If f prime is a continuous function on the closed interval a to b, then the integral from a to b of f prime of x is equal to f of x evaluated from a to b, which is f of b minus f of a. And this relationship is known as the fundamental theorem of calculus, FTC. Evaluate using the fundamental theorem of calculus without using a calculator. A definite integral always gives you a number answer, so we will integrate and then evaluate from a to b. I'm going to rewrite this as a power and then integrate using the power rule for integration. Add 1 to the power, that's our denominator, and 2 is just a scalar. This resulting function we will evaluate from 0 to 4. Simplify. In AP, it's very important that they see the subtraction of evaluating from the upper limit and evaluating from the lower limit. What do I mean by that? I can't just stop right here. Yeah, I know when I plug in 0, the rest is going to be 0, but they need to see subtraction. And now we'll simplify. There's our answer. Here we have a function of t to a power, so we will use general power rule for integration, or reverse chain rule. What that means is we need to establish u, find u prime, and make sure u prime is present in the integral before we can integrate. U is the function of t, or function of x. U prime is equal to 4, so 4 needs to be in our integrand. I'm going to multiply our integrand by 4 and multiply the outside of our integral by 1/4. This is just multiplying by a special form of the number 1 to make sure 4 is in our integrand. Now we can integrate. Add 1 to the power, and that's our denominator, evaluated from 0 to 1. You could distribute in the 1/4 now or distribute it in later. I will distribute later. Plugging in the upper limit, subtraction, plugging in the lower limit. Here is the answer. For number 3, I could definitely check, can I use the reverse chain rule? But the derivative of 2x minus 1 is 2, and I have an x here, so no, I cannot. So we're going to have to use u-substitution. U is equal to the radicand. Solve for x. Derive x with respect to u. And solve for dx. I'll rewrite this integrand as a product. Now we're going to substitute out all the x's and replace them with u's. But I have a problem. These limits, my lower and upper limits of the integral, are in terms of x. They are not in terms of u. So I cannot write 1 and 5 here because I don't know if 1 and 5 are still my limits in terms of u. In fact, most of the time, those limits have changed once you use u-substitution. So you have two options. Put a question mark for your lower and upper limit for every step until you substitute back in x, and then you can use 1 and 5. Or you have a relationship, a known relationship between u and x. You could substitute your lower and upper limits and find the new lower and upper limits in terms of u. I'm going to show you both ways, but first I'm going to show you how we would change our limits. The relationship between u and x is this. So to find the lower limit a, we would plug in the lower limit 1 for x and find a in terms of u. To find our upper limit, we would plug in the upper limit, 5. The lower limit is 1, the upper limit is 9 in terms of u. Let's simplify the integrand. This 1/4 I can take out of the integrand, and I can distribute so that all I have to do is use power rule for integration. The integral is u to the 3/2 over 3/2 plus u to the 1/2 over 1/2 evaluated from 1 to 9. Simplify inside. Plug in the upper limit. AP has to see this subtraction symbol. And simplify. All right, 16 over 3 is the answer for this definite integral, and that's how you do u-substitution with a definite integral. If we had not changed our limits into terms of u, getting 1 and 9, we would have had question marks for all of these numbers up until this step. Then we would change these u's to be x's, and then we'd be able to put the previous limits of 1 and 5 and plug them in, show the subtraction, and get our definite integral. Start Plus Accumulation Method. There's actually a nickname for this. What do you think people call it? That's right, spam. But you will almost always hear me refer to it as Start Plus Accumulation Method because if you start to use an abbreviation too soon, sometimes you forget what it's actually standing for. This right here is the fundamental theorem of calculus. But guess what? This equation is a true equation, so I could rearrange it and I would still get a true equation. If I added f of a on both sides, then I could get f of b is equal to f of a, the function at the lower limit, plus the integral from a to b of the derivative of f with respect to x. Just a rearrangement of the fundamental theorem of calculus, but very important because sometimes they will ask for a function value and you may not know what that function value is, but they may have given you a different value and an integral or a graph in a way that you could find this missing piece. So this means a function value can be used as a starting value plus a definite integral. Start plus. Get it? This is the start, this is the plus. And integrals are also known as accumulators. Here's the derivative, not the function, and here's one function value and they're asking for another function value. So here is my lower limit, here is my upper limit. So they want me to find f of 2 by taking f of 0 and adding the definite integral from 0 to 2 of f prime. F of 0 is 4, so I'll plug in 4. And then I'll integrate x to the 3 over 3 plus 3x from 0 to 2. Simplify. Evaluate the definite integral. Be sure to show that subtraction. F of 2 is 18. If an object's velocity is v of t equals 2 to the t, and s of 2 equals 8, find s of 3 and use a calculator. My lower limit is 2. My upper limit is 3. The velocity, or the f prime equation, is 2 to the t. So start plus accumulation method should look like this. S of 3 is equal to s of 2 plus the integral from 2 to 3 of our velocity function. Now we plug in. S of 2 is 8. V of t is 2 to the t, d of t. And because this involves a definite integral, we can use a calculator to evaluate this. I used the math menu and I got 5.770780164. So my answer is 13.771 or 13.770. Now it's time to evaluate the definite integral for absolute value. And we don't have a formula for integrating absolute value. Whenever we have an integral of absolute value, we want to think of it as signed area. And remember that making a function absolute value means reflecting all y values that are below the x-axis to be above the x-axis. So if k of x is the non-absolute value version of this function, just so I get a picture, this is a parabola that's been shifted down 4. Now let's graph the absolute value version of that. We'll call it f of x. Our goal is to take the integral, or find the signed area, between the curve and the x-axis from 0 to 4. I'm going to split our existing interval, and this is how. From 2 to 4, the green graph and the purple graph are the same. So from 2 to 4, I can take the integral of the green graph, and it will still give me the integral of the purple because those graphs are on top of one another on this interval. But I also need to add this area to it. And what is that area? Which points were reflected from below the x-axis to be above the x-axis? Well, the points from 0 to 2. So from 0 to 2, the green graph is down here. But if I could reflect this green graph, then I would get the purple. How do you reflect over the x-axis? You multiply the entire function by -1. Anytime you integrate absolute value, you'll need to figure out if there's a split in which a piece of the function must be written as the reflected version of the original argument, the thing inside the absolute value. Now I can integrate. That's evaluated from 0 to 2. And that's evaluated from 2 to 4. So the red and yellow area, the area under the curve between the curve and the x-axis, is 16.